All right. In the last lecture, and at the end, we talked about perfect graphs. So a simple graph is perfect if for every induced subgraph, the chromatic number is equal to the Killing number. And there we have seen 4 examples. So one is bipartite graphs, and the other is line graph of bipartite graph. And then there's a complement of the line graph of bipartite graph and complement of bipartite graph. And you see that there's some kind of symmetry, right? If you have a class of graphs which is perfect, then it seems like in all these examples, we only saw 2 examples, but in all the examples, the complement is also perfect. And there is no obvious reason why being a perfect implies that complement is perfect, right? So when you see this proof, so line graph of bipartite graph is perfect because of Koenig's theorem, right? Edge chromatic number is equal to the maximum degree. And complement of line graph of bipartite graph is perfect because of another Koenig's theorem where tau is equal to nu on the bipartite graph, right? And there's no immediate correlations. Right. Bipartite graph is perfect because chromatic number is 2, Killing number is 2, as long as you have an edge. And complement of bipartite graph is perfect because of Koenig's theorem, right? Alpha plus tau is number of vertices. So it's again a bit strange. And that was actually a conjecture by Berge. It was a weak perfect graph conjecture. So if graph is perfect, then the complement of graph is perfect. And we now have a strong perfect graph conjecture, which is now a theorem. The graph is perfect if and only if it doesn't have any other cycles as an induced. It doesn't have any other hole. So hole is a induced cycle of length at least 5. And odd hole means length is odd. Or antihole, no other antihole, where the antihole means complement of hole. And odd antihole means the length, the number of vertices is odd. So the strong perfect graph conjecture implies the weak perfect graph conjecture, and the weak perfect graph conjecture we will see the proof. And that was proved by Lovász, so theorem. In 1972, a simple graph is perfect if and only if its complement is perfect. And there was a famous story. So Lovász is still alive. And in 1970s, he was very young. He's a Hungarian mathematician. He used to be a professor at Yale, and then he became a permanent researcher at Microsoft Research in Seattle. And then he went back to Hungary, and he's currently the head of Hungarian Academy of Science, I think. And he's still working, but in 70s he was very young. So one of the famous mathematician in that area is Fulkerson, and the Fulkerson was working on this conjecture for a while, but at some point he gave up and was thinking of the counterexamples. And then one day he got a postcard saying that a young Hungarian mathematician named Lovász solved it. And then in that afternoon, Fulkerson was also able to prove this weak perfect graph conjecture. So in mathematics, sometimes it helps you to know that, if you know that the theorem is true, then maybe you can immediately prove things. Anyway, that was an old story. So I'm going to show you a proof by using this nice characterization, also due to robots. It says the following: a simple graph G is perfect if and only if number of vertices of H is at most alpha H times omega H for all induced subgraphs H of G. Why is this meaningful? Well, let's see. What happened is, right, this direction, that's each direction. So if graph is perfect, then the chromatic number is at most, no, it's equal to Kling number, right? Do you remember what the definition of alpha? Alpha is the maximum size of stable set, right? It's a set of vertices pairwise. Maximum stable set is a set of vertices pairwise, non-adjacent. And if you can color a graph by k colors, then one of the color class has size at least n over k when n is the number of vertices. Because if you have a graph and you color by k colors, and by pigeonhole principle, one of the color class, one of the stable set formed by vertices of the same color will have no edges between them, so it's stable. So alpha of graph is at least number of vertices divided by chromatic number. This is true in any graph. So when you multiply that, you get the inequality that you have. So in any graph, number of vertices is the most, no, in any perfect graph, number of vertices is the most alpha times omega. So for the only non-trivial direction is the backward direction. Okay. Now here's a claim. If G is minimally imperfect, so meaning G is not perfect, but when you delete any vertex, it becomes perfect. Okay, then when you delete the stable set, you keep the same Kling number. Why? So it's not perfect, so chromatic number is not equal to Kling number. So chromatic number is strictly bigger than Kling number. Now when you delete the stable set, okay, so I should say use non-empty, because if you, if you use empty, it's trivial. Okay, so we may assume use non-empty. Right, so when you delete the U, then certainly it became a perfect graph. Right? Because G delete U is perfect. Now, we have this inequality, right? But how big is the gap? Right? When you delete some set, the Kling number decreases. Cannot increase. When you delete the set, a stable set, chromatic number could decrease, but it cannot decrease by 2. So the gap is at most 1. Here the gap is at most 1. Right? So the difference is at most 1. Now, you had this 2 equal number, and when you add a 0 or 1, you have different number. How is it possible? The only way it's possible is you add 0 here and you add 1 here, right? So that means chromatic number, no, Killing number of G is equal to Killing number of G delete U, and chromatic number of G is chromatic number of G delete U plus 1. Okay? So that's why Killing number of G delete U is equal to the Killing number of G. Okay? Now, we're going to use this claim to prove the claim. Prove this Lovas's characterization of perfect graphs. So, suppose G is minimally imperfect. And let's pick set S consisting of V1, V2. Alright, so let's say I just need a notation. So let alpha be the alpha of G and omega be the omega of G. So let S0 be V1, V2 up to V alpha be a stable set of size alpha. Now, I know that omega of G delete Vi is equal to omega of G, and chromatic number of G delete Vi is equal to chromatic number of G minus 1, right? By the same reasoning. Right. And these two are equal because the graph is minimally imperfect. So when you delete Vi, graph becomes perfect. All right. So what does that mean? So this is equal to omega. Well, I mean, I don't need the. Okay, let me say that. So that means G delete Vi can be partitioned into omega many stable sets. But right, the V of vertices of VGI, G delete Vi can be partitioned into omega many stable sets for each I. Right? So for every I, when you delete Vi, the remaining can be partitioned into omega stable sets. So, right, so you have a V1. Okay, I mean, let's not try to make a picture. But so that means I had a S0, that's initial set, and then I have a S1, S2, S alpha, no, omega for V1, for partition of VG delete V1, and then S omega plus 1, S omega plus 2, up to S2 omega, that's a partition of VG delete V2, and I continue. And then there will be partition of VG delete V alpha, so that is like, right, so alpha omega, right, so alpha minus 1 omega plus 1, it's alpha minus 1 omega plus 2, until you have 2 alpha omega, right? So we have a many stable set. Oops. So we obtain alpha omega plus 1 stable sets of G, right? What are the property? So this is S0, S1 up to S alpha omega, such that. Now let's look at the vertex, right? How many times the vertex appear? if a vertex is not in S0, right? If it's not in one of these V1 up to V alpha, then it will appear in every, it will appear in this tuple exactly once. So the vertex that does not appear in S0 will appear exactly alpha times. If a vertex appear in S0, so let's say Vi, how many times does Vi appear in this list? Well, it appears here once, but it doesn't appear in the partition of G delete Vi. So again, the number of times the vertex Vi appears in this list is exactly alpha. So each vertex of G appears exactly alpha times. Right, I don't need the number 1. All right, so we got the list of stable sets. All right, now we're going to use the claim. When I delete the stable set, I can find the clique. By the claim, omega of G delete Si is equal to omega of G, which is omega. So graph, so there is, yes, so for each I, 0 up to alpha omega, there is a clique Ci, right, such that Ci intersection Si is empty, and the size of Ci is omega, right? Now, when you look at the Ci intersection Sj, what happens? Well, if you have a clique and stable set, you cannot have a intersection of size 2, because clique is a set of pairwise adjacent vertices, stable set is a set of pairwise non-adjacent vertices. You cannot have 2 vertices in common. So this is always at most 1 for all ij. Now, what's gonna happen then? Now, every vertex appears in exactly alpha sets in S0 up to S alpha omega, and each Ci has size exactly omega. So that means each Ci, every Ci has size exactly omega. Now, when I add this thing, Ci intersection Sj for all j from 1 up to from 0 to alpha omega, right? What's gonna happen? I know that every vertex in Ci appears exactly alpha times. So this is gonna be alpha times omega, right? Because of that property, and also because of that, right? Every vertex appears in exactly alpha times, and if a vertex appears in some Sj, then no other vertex of Ci can appear in Sj. So this number is exactly alpha times omega. But oh, maybe I didn't use it. Yeah, precisely. More precisely. This one is enough. All right. Now, we know that this is at most alpha times omega. Why? Because this is at most 1 at all the time. And I know that Ci intersection Sj is empty. The Si is empty, right? So at one place you have 0. So this means you have equality. So Ci intersection Sj is always not Sj is 1, 0. If I is not equal to j, it's 1. If I is equal to j, it's 0. Right? So we have a set, right? S0, S1, S2, S alpha omega, and C0, C1, C2, C alpha omega. Right? We have stable sets and we have cliques. Now we're going to use linear algebra to finish the proof. It's a cute proof where you can use basic linear algebra to prove something on graph theory. Alright, so how are we gonna make it? So we make one matrix where the number of rows is like S0, S1. So you have alpha omega plus 1 rows, and then the vertices, the columns are indexed by the vertices of the graph G. And then you put 1 if some Si contains the vertex on this column, then 1 or 0 otherwise. Okay? So that's one matrix. So this is my, let's say this is M. So M is a matrix Mij, where the I is indexed by so that M and I is indexed by the 0, 1 up to alpha omega, and the J is indexed by vertices, and Mij is 1, 0 if J is in Si, and otherwise it's 0. Right? Now I do the same thing for N. N is, but now it's indexed by cliques. Right? Similarly, N is Nij. Okay, so Nij is 1, 0. 1 is if J is in Ci, and otherwise 0. Now I constructed two 0, 1 matrices. Alright, now why do we care about these matrices? They have the same number of columns, so I can multiply them. M times N, I mean, as long as I make a transpose of one matrix, right? So what is this consequence of the M times N transpose? Right. What happens is, right? So you multiply these two matrices. Now let's look at the ith row, j's column of the product. So ith row and j's column, right? So what we do is we take this column vector and make transpose and make we multiply this with that. Now if you have a 0 in both coordinates, so if you have a 0 here, 0 there, then they meet and they still form 0. So what's gonna happen? Well, what happens is if you have 1 and 1 at the same location, then it will add up. Otherwise, it's not gonna add up. Right? So this is the you can see that this is a matrix, right? Precisely describing the intersections, right? So I is from 0 up to alpha omega, and j is indexed by, I mean both ij are in this range. Okay, let me just say, right? So each matrix entry is just intersection of Si and Cj. Now we know exactly what this matrix is. This is a matrix where the diagonals are 0 and all other entries are 1. Okay? So that's the matrix. It's a square matrix whose number of rows is alpha omega plus 1. Now, what is the rank of this matrix? Right? This matrix has rank. Do you remember the definition of rank? Rank is the dimension of the span of the column vectors. And these vectors are linearly independent, so the dimension is everything. So this rank is alpha omega plus 1. Now, here's the thing. Rank of m and t is always less than or equal to rank of m. Or, I mean, I can say rank of n transpose. It doesn't matter. Maybe it's, I mean, let's, okay, n transpose. Why? Because rank is the span, dimension of the column space, which is the span of the column vectors. And the column space of m times n transpose is a subspace of the column space of n times n transpose. Because column space of n transpose is a linear combination of the columns. Each column vector is a linear combination of column vectors of n transpose. And rank of n transpose is at most number of rows. Number of rows of n transpose, which is the number of vertices. So alpha omega plus 1 is less than or equal to number of vertices. Wait, so then what does that mean? That means number of vertices of graph G is at least alpha omega plus 1. Right? So that means, what does this mean? This means if you have a minimally imperfect graph, the number of vertices is at least alpha times omega plus 1. So why does this prove our claim? I mean, our statement that we wanted to prove the following, right? So graph is perfect if and only if number of vertices of any induced subgraph is at most alpha times omega. So if you have a graph which is not perfect, then it must have induced subgraph which is minimally imperfect. And that induced subgraph will violate this inequality. So that's the proof. Okay? So this proves that this proves this weak perfect graph conjecture. And the proof of strong perfect graph conjecture is completely different. It's very complicated actually, and has more than 170 pages. And the proof is more like characterizing simple graphs having no induced, no other hole, and no other antihole. But it doesn't give exact characterization. It also assumes that it's a minimum count example to the strong perfect graph conjecture. And more precisely, what it does is it proves, what they showed is they prove that every simple graph without odd hole and odd antihole can be either decomposed into smaller pieces by certain decompositions, or it's one of the basic graph classes. And then it was known that each of these decomposition cannot appear in the minimum count example, the strong perfect graph conjecture. And also, each of these basic graph classes satisfy the strong perfect graph conjecture. So that by combining that, it proved the strong perfect graph conjecture. Okay. All right. So that's the that's about perfect graphs. Now let's move on to the next chapter. Nowhere is there a flow. So this is probably the first place where we will talk about directed graphs. Oh, except yeah, we mentioned directed graphs in the proof of this theorem that chromatic index is equal to the least chromatic index. But anyway, so let's start with the directed graph. And yeah, so if you have an edge, then right, so then you draw it like this. This is tail. No. Yeah, so yeah, okay, this is tail, head, right? So delta plus v is the set of edges having v as its tail, and delta minus, so it's outgoing edges. Delta minus v is the other one, set of edges having v as its head. Okay, now what we're gonna do is to make a definition of something like this, right? So you have like you can think of the water networks underground in the city where nobody consumes any water. So let's say, for instance, the water flows this direction with amount 1, and then it flows from here with amount like maybe 2, but then there's this direction with 1, and maybe here's 3, so 2, and then let's say, oh, this is 1. So nobody consumes anything, nobody supplies anything, so it's water circulates whole network. Okay, so this is, so I need to send 4 because for this vertex 3 and 1 are going out, so I need to send 4. And here is 2 is coming in, 4 is going out, so I need to send 2, and 3 is coming in, 1, 2. Okay, so maybe 1, 1. All right, now only one edge remains, and for this edge now I have a 1 so 1 coming in, 2 goes out, so maybe this direction I have 1. All right, so this is one instance of something called the circulation. All right, so let me define it. A circulation. Okay, let me write. Okay. G is a function phi on the set of edges to, let's say, real numbers. So we allow negative numbers such that for every vertex, the sum of the outgoing edges is equal to sum of the incoming edges. right? So then we call it a circulation. And then we define a no-weather K flow. So for a positive integer K, a nowhere zero K flow of G is a circulation phi such that phi e is, or the absolute value of phi e is equal to 1 to up to k minus 1 for every edge. Okay, so you never use 0, you only use plus minus 1, plus minus 2, plus minus 3, up to plus minus k minus 1, then we call it a no-weather K flow. And it's easy to see that any undirected graph has no-weather K flow for certain orientations. No. What I mean is, okay. What I mean is, this is written in terms of directed graph. Now, what about the undirected graphs? Okay, so we say an undirected graph G has a nowhere zero K flow if any of its orientation has a nowhere zero K flow. So if you have an undirected graph, I put any direction, arbitrary direction. So orient the graph as I like. And if any of them has a no-weather K flow, then we say the graph has no-weather K flow. And what I wanted to say was that if any one of the orientation has no-weather K flow, then all of the orientations have no-weather K flow. Because if you have an edge like this, then when you reverse it, you can simply replace 1 by minus 1. Just multiply by minus 1, and that's no-weather K flow again. So, like even though I said it's any of its orientation has no-weather K flow, I could say that all of the orientations have no-weather K flows. All right. So why do we care about no-weather K flow? That's because of this proposition. Okay, so let G be a plane graph. Then G has a nowhere zero K flow if and only if its geometric dual is K colorable. All right. So for plane graphs, the graph has no other K flow if and only if its geometric dual is K colorable. And as you remember, one of the most interesting open problem in graph theory was the 4-color problem. Right? Now it's known, but so people studied no-weather K flow because it's kind of generalization of no-weather of the chromatic number on the plane graphs. Right? Instead of proving that planar graphs are 4-colorable, we could try to prove that its dual, still planar graphs, have no-weather K flow. So why is this true? Okay. So let's see the backward direction first. Alright, suppose that the geometric dual is k colorable. That means you have a vertex in the dual, right? I mean, each vertex in the dual has a color. But vertices of dual correspond to the face. So for each face R of G, let alpha R be the color. Be the color of the vertex in R, vertex of the dual in R, right? We fix the K coloring, so every face has a color. Now let's say, for instance, this face has color 1, this face has color 2, etc. Now we orient edges as we like, so we assign directions to every edge. Okay, so for instance, directions. Now for every edge, E of G, let phi of E says alpha of R1 minus alpha of R2, where R1, R2 are faces incident with E and R1 is on the left of E and R2 is on the right of E. What do we mean by left and right? Well, now we have direction. So then R1 is here, R2 is here. Okay, so that's the direction. Now I want to say that this is a circulation. Phi is a circulation. Why? Let's look at the vertex V. So you have some incoming edges, some outgoing edges, incoming, outgoing. It could be mixed, and we have a faces R1, R2, R3, R4, R5, etc. RL. Now, being a circulation, the property of being a circulation doesn't change if we reverse it, right? Because when you reverse it, this becomes a new R1, right? So this phi was like R1 minus R2, left minus right. Okay, I mean, let's say, let me give you an example, right? If this is color 1 and 3, then this was 1 minus 3, it's minus 2. Now if I reverse it, then this becomes 3 minus 1, which is 2. Again, when you reverse an edge, if you multiply minus 1 to the value, being a circulation, the property of being a circulation is preserved. So we can assume that, to simplify the situation, we can assume that everybody is incoming just by reversing. Then you have R1, R2, R3, R4, etc. R5, Rn. Now, what are these edges? So this one, for instance, left minus right is R1 minus RL, left minus R2 minus R1, R3 minus R2, R4 minus R3. So we are adding these things. So what we are adding is, okay, I mean, I should say phi R1 minus phi R2. Right? So what we are adding is phi of R1 minus phi of R2 plus phi of R2 minus phi of R3. So the sum of the values of the incoming edges is all these sums and then last one is minus this. Oh, did I do the other way around? Yeah, it's left minus right. Okay, so since I draw it in the clockwise order, all right. Yes, this R2 minus R1, R3 minus R2, and we are adding this RL minus RL minus 1, and then R1 minus RL. So these are the values. Okay, oh no, this is not that. Alright, so these are alpha. Right, the color. And that's 0. And there's no outgoing edges. So that means phi is a circulation. Furthermore, phi of E is always in 1 to k minus 1 because it's a difference of two numbers, two colors. And adjacent things have different colors. Right? It was coloring, and in the original plane original graph coloring, two adjacent vertices get distinct color. Therefore, in the geometric dual, right? I mean, these two faces always have distinct colors because it was colorable. And this is place where I mean, this is one place why I define graph to right. I mean, yeah. So when you define the coloring of the graph, I actually wanted to say that if graph has a loop, we don't have any k coloring. Right? Because otherwise, loops in the geometric dual will correspond to the cut edges in the G. And if you have a cut edge, then both faces are same. So you can never have a, I mean, this construction will give you phi value to be 0. Right? Does it make sense? So I always make sure that right, these two faces have distinct colors whenever they are adjacent. So what happens if they are same face, right? Right. If you have a edge and happen to be that this R1, R2 were same face, then am I giving 0? Right? But in the dual, what happens is they are same face, it's a loop. Right? So this is this side, this is an edge, right? And we define coloring so that a graph with a loop is not k colorable for any k, because the vertex is adjacent to the same, so we don't want to call it colorable. And that that is convenient for us because that allows us to say this proposition more nicely. All right, how about the other direction? Suppose I have a noisy K-flow. How do I get a coloring? I fix a face P, F. Okay, so here's a face F. Now there's a face G. For any face G, there is a curve from F to G, right? So I can always find the curve from F to G. Or let me put it this way. What does that mean? So we know that geometric dual is connected, right? Now let F be a fixed vertex of the dual, and we define the color of F to be, let's say 0. Why not? Now we need to define the color for the whole graph. For any vertex V in the dual, there is a path. Oops. From F to V. So here's a vertex F, there is a vertex V. There is a path in the dual because the geometric dual is always connected. Now in G, those edges are actually crossing edges of G, right, with certain directions. So we define, so let's say the path P is like F E1, V1, E2, V2, okay, star, E, I don't want to use, okay, E L star, V, right, and then P intersect E1, E2, EL of G, right, so those are E1, E2, EL. Now what we do is to define C of V as the sum of the phi value of EI if EI goes from the, okay, I mean, how do I right, let me just say, oops, sum of the EIs where EI is from the right to the left of P, and minus EI where EI is from the left to the right, because we have orientation. So here's a path P, right? Some edges cross this way, so those are the edges that we're gonna subtract. Some edges are coming from left to right. Yeah, oh, this is right to left, right? According to the direction of P, this is right to left and left to right, right? Then we are subtracting. Now we claim that this is consistent coloring. but you never know whether it gives a coloring. So let's do C modular K gives a coloring. So why? So why is it consistent? What if I have two paths, P1 and P2, right? So F3. If I have two paths, right, and then I have vertices going, edges going out, edges coming in, edges going out, edges coming in. And then you have one value obtained by P1, one value obtained by P2. And I claim that both values will give the same number. Why? Because when you combine them, you have a closed walk. Actually, for any closed walk, let's say C of the dual, okay, for any closed walk, the sum of the edges going left to right is equal to sum of the edges from right to left. So if it's true for any closed walk, then this is consistent, because when you have a two paths, then on one path, when you have two paths, then you can reverse one path, and then left to right becomes right to left, right to right become left to right, right? And then because of these equations, you have the same thing. Right, so we have two directed paths. Instead of that, you consider this thing, and then we apply this statement. Then what you end up is this will be equal. So why is this true? Because phi is a circulation. Right, so phi of E for any vertex outgoing, the amount of outgoing is always equal to amount of incoming. So now for X, for any set X, the sum of this thing is 0, right? Because it's adding zeros. Now let's look at this equation. What's happening? You have set X outside. For every edge inside, the value of phi is added once and then subtracted once. So they cancel each other. So what end up is only those edges are counted, right? So this is equal. So this implies the sum of the edges going out of the set is equal to sum of edges going into the set. Okay, well, delta plus X is the set of edges having its tail in X, its head not in X. Delta minus is the other set of edges having its head in X, its tail not in X. Right? So whenever you have a circulations, this sum of this thing is equal to sum of this thing, right? So sum of edges going out of some fixed stack X is equal to sum of edges coming in. So that means in the geometric dual, if I have a cycle, then I look at the vertices inside in my G. So this is a cycle in the geometric dual. So these are vertices of G inside this cycle C. And C is a simple closed curve. So you can distinguish inside and outside by Jordan curve theorem. Now, by this thing, so the sum of edges going out is equal to sum of edges coming in. Right? By this statement. So this is true for any cycle. And whenever you have a closed walk, you can decompose it into cycles. All right. Whenever you have I think now it's an easy exercise to prove that any closed walk, of course, if you repeat the same edge many times, you have to add this many times, right? It's a good formulation. Yeah, okay, right. Right. So I should say like EI, right? So C is like V0, E1, V1 up to EL, VL. So yes, EI. So for the cycle, this is true, so you can easily generalize to a closed walk. Now that means whenever you have two paths, we end up with the same number. So this number is well defined. Now, why is it a coloring? So if you have two vertices which are adjacent, if VW are adjacent in dual, now, and let's say this is a path, and let P be a path from this fixed vertex to V, then we can add the P with this as VW is a path or I could assume that this path. So suppose VW is adjacent in G, let P be a path. We may assume W is not on P. Otherwise, swap VW. Okay? Now, P plus VW is also a path from F to W. I don't have to say also. P plus VW is a path. So then, it's easy to see that CW, color of W is just color of V plus minus phi of VW. Right? And phi of VW is in plus minus 1, plus minus 2, up to plus minus k minus 1. So CW is not equal to CV modulo k. So C modulo k is a coloring, k coloring of the geometric dual. Right? You may wonder, what happens if I have numbers bigger than k? Okay, let's not worry because we're gonna take a modulo k. So just divide by k and take a remainder. Then you only have colors from 0 to k minus 1. And that is k coloring of the geometric dual. All right? So in a certain way, nowhere zero flow is a continuation of graph coloring. So later we will see many more properties, and some of them will be striking, very different. Okay, so that's it.